So let's take a second to talk about radicals. Square root of 1. This is something that in middle school you probably would have said is 1. And in Algebra 2, maybe you would have jumped up to the level of, say, it's plus or minus 1. But now that we've played around with complex numbers, we can actually learn to rewrite that 1 as 1 plus 0i. And we also have a negative 1 plus 0i. At first glance, that seems like a whole lot of work for very little gain. But what putting these two numbers in the complex plane allows us to do is see symmetry. We'll go ahead and let this one be blue, and we'll let this one be green. So note that we have those two numbers. They are both entirely real numbers, and there they are chilling on that complex plane. Note that they are 180 degrees apart, or pi radians, either direction. Not super exciting, let's be honest. You can play that same game with the square root of negative 1, only now your two roots are going to be plus and minus I, entirely real or entirely imaginary numbers. Once again, still just 180 degrees apart. So far, it's kind of like, yeah, so what? We knew that already. Why would we plot them? What makes this exercise interesting is now we can start looking at other radicals, things that we haven't really played with a whole lot, like, what's the fourth root of 1? Well, an Algebra 2 student will still tell you the fourth root of 1. There's going to be a positive 1, and there's going to be a negative 1. But the fundamental theorem of algebra tells us that if x to the fourth power equals 1, there are actually 4 solutions in the complex plane. We've only found 2 of them, a positive 1 and a negative 1. So when we go to take a look at that complex plane, we found this one, our positive 1, and we found this one, our negative 1. We can take this idea of symmetry and use it to help us find the other 2 real or imaginary solutions to the fourth root of 1. It turns out that if you break that plane up into 4 chunks, I wonder why 4. It turns out if you break that plane up into 4 chunks, you can actually find those other 2 solutions. It turns out positive I and negative I are also fourth roots of 1. And note, there's still symmetry. It's a different kind of symmetry. We're now looking at 90-degree increments in that complex plane instead of 180-degree increments. But there is still symmetry. If you don't believe me that those are fourth roots of 1, well, just start multiplying. Keep in mind, if we are claiming that I is a fourth root of 1, that means I times itself 4 times equals 1. Well, I times I is negative 1, I times I is negative 1, and negative 1 times negative 1 is just 1. So certainly that does check out. So symmetry can be a great tool for solving equations. In Algebra 2, you were able to find 2 solutions, but there are actually 4. We were missing 2 of them because we didn't have this idea of the polar plane and symmetry. And maybe an advanced Algebra 2 student could have figured that one out on their own. What makes things difficult is when we start talking about cube root of 1, or fifth root of 1, God forbid, the 7th or 9th roots of 1. Very difficult to imagine breaking up that complex plane into 3 sections. But we can do it. We still get our whole number 1, of course. One of the cube roots of 1 is just 1. Again, that's the one a middle school student could have found. But the other 2 are a bit more complicated. So when we break that complex plane up into 3 chunks, each one of those chunks needs to be 120 degrees. And so trying to find those other 2 roots land us square in those quadrants there inside the complex plane, numbers that are not wholly real but also not wholly imaginary. they are complex. And we are actually going to have two complex roots of the number 1, and they are going to be negative 1/2 plus root 3 over 2I and negative 1/2 minus root 3 over 2I. Those are more difficult to find, and at first glance, if you're like, I don't believe you. Pull up a calculator, double check. If you cube that ugly complex number I just showed you, the solution will be 1. Negative 1 plus root 3 over 2I is 1. You change the sign, you still get back a 1. So finding these roots, these other solutions to that, and the question, what are the cube roots of 1? That is the goal of polar coordinates. They allow us to visualize that symmetry, and so that's kind of what we're going to start looking at. Of course, I'm not expecting anybody to come up with this stuff just in your head off the fly. There is a formula for this. We'll take a look at that in the next video. But just kind of the overall goal of hey, what are we doing? What's this formula from? What's the big idea here? We're breaking that complex plane up into different chunks, and we can use this idea of polar coordinates to see that symmetry. So in the next video, I'll introduce the formula, and we'll actually find stuff like this. See you then.